is CNI Carbon Neutrality Institute seminar today. As I just have mentioned before, today we have invited Professor Soryong Chae from University of Cincinnati. Let me give you a very brief introduction about today's speaker. Professor Soryong Chae has earned his PhD degree from the Department of Civil and Environmental Engineering at KAIST in 2004, and then he has moved to the state, and he started his first faculty career from 2011 as an lecturer at University of Sydney, Australia, and after that he has moved to University of Cincinnati and started his assistant professor career from 2015, and until now he is serving for the same university, and he is now an associate professor with tenure at the University of Cincinnati. Today he is going to share his insight into resource recovery from wastewater, from water and waste. Professor Chae, please.
Yes. So may I proceed?
Yes, if you're ready, you may start.
Sure. Thank you so much, Professor Lee, for the nice introduction. Let me share my screen. All right. So can you see the full screen?
Yes.
All right, thank you so much. So again, thank you for inviting me for this nice seminar. And also I appreciate for your presence, even it's almost the end of the semester. I know everybody is busy, but thank you for coming, for this seminar. So today I will talk about very, very big topic and broad topic, which is grand challenges and opportunities for circular economy and carbon neutrality. But I will focus on water and wastewater for resource recovery. So I believe Professor Lee gave us very nice introduction about my academic career. On the top of that, I'm serving for a couple of journals, and I'll introduce how I can contribute, through my academic career and also society by serving this journal. So that will come at the end of the slide. So here is my table of content for today's presentation. So I will start from the global warming. Already you knew about this one and greenhouse gases, but I want to recap you because it's a very important topic to make my story start. And also I will talk about greenhouse gases from mining and resource recovery. And I'll move it to water scarcity and water quality. One is the quantity issue, the other one is quality issue. So we'll cover some challenges and opportunities related to this water. And lastly, I'll introduce about my research interest and outcomes. And finally, hopefully we have some time before lunch for you having some Q&A session. So let me start from this slide. I believe you see this figure maybe not a million times, but many times. So this graph shows how global surface temperature changed over the time. If we compare average temperature between 2011 and 2020 versus 1951 and 1980. So if any color presented as a white color means it's the same temperature between two periods, but if any color move to yellow, orange, and red and dark brown, that means our global surface temperature increased compared to the period between 1951 and 1980. So if you see this figure on the left, all this global continent, has, almost, orange or red color. That means temperature goes up. But where it comes from in terms of the temperature change, we can see this very long-term, monitoring of global surface temperature. This green line indicating if we don't have any industrial activities, this natural drives our temperature keep around certain level, but human added some temperature increase on the top of that. So finally, we see this black observed temperature goes up ever and ever. So the difference between this green line and this black line indicating contribution of human activities to the temperature increase. Is not very significant, but even 1 or 2 Fahrenheit temperature change, or even 1 degree Celsius change makes a huge difference, as you know, like a climate change, right? So today I'll focus on some materials and also global house gases from mining activity. Then I'll introduce how we can reduce minimize that greenhouse gases emission from mining activity by recycling or reuse some material. So again, the left graph already I explained that one, and I want to move to this summary table on your right. So this table shows the from beginning to the end of material life cycle assessment, focusing on the greenhouse gas emissions. So if you see here on the very first column, we have a list of material, metal, gold, titanium, aluminum, nickel, and other material. At the end of this one is steel. And the last column showing that the greenhouse gas emission, million metric ton of carbon dioxide equivalent per million ton of metal produced. So if you see here, gold metal, we expect about 27,000 million tons of carbon dioxide discharged or produced by when we produced or when we prepare 1 million ton of gold, which is a very high number. And it decreased if we move to the bottom of the table. And for the steel production, only 2.3 CO2 will be produced per million ton of steel. However, if we think about the production scale, gold material annual is back to 2020. If you see this number, annual global production is only about 0.0035 million tons. Then steel is about 1,880 million tons. So when you combine these two numbers, 26,000 times 0.0035 versus 2.3 times 1,880, the total carbon dioxide emission much greater from the steel compared to the gold. So there is the very important message for us how or why we need to manage or reduce the carbon dioxide emission from some specific metal production. And also, if we move to the fertilizer is very essential for agricultural activity. Let me start my video again. For some reason, it's turned off. I'm sorry for that. So for some reason, we need some fertilizer to grow our plant and crops. So if you see this number, if we produce 1 million ton of nitrogen, of course, it depends on the production system, like our Borsche process or other manufacturing system. Usually we see 1.9 to 7.8 million ton of carbon dioxide will be discharged. And for the phosphorus, a little bit lower, but still 2.3 to 4.5 kilogram CO2 can be released per kilogram of phosphorus. So this number is significant compared to this number on the table. And annual global consumption of this fertilizer is about 224 million ton. So this is not a small number. When you combine these two terms, you can imagine how much carbon dioxide can be generated from this fertilizer production. So one way we can reduce this carbon dioxide production will be to recycle this material, like metals and the fertilizer from somewhere, and we can globally reduce this carbon greenhouse gas emissions. So let's move to the next one. Okay, and also there are other important elements. If you see here, this all light blue or dark blue indicating a rare earth element. And if you see this one, atomic number somewhere around 57 to 62, we classify the light rare elements, and the bigger number heavy element. But key point is those materials are very popular nowadays for our life. If you see here, for electric vehicle and also, other type of, novel transportation, vehicles, they use a lot of batteries and also a lot of, rare earth element. And also when we produce renewable energies like wind power and the solar light, and even kind of fuel cells, it includes a lot of different types of fuel cell. Still, we need a lot of this rare earth element. And if we will see the global reserves from different countries, China has a lot of maybe relatively more rare earth element than other countries, and also Brazil, Vietnam, and Russia. United States only 1.4 million tons. But I don't know where is the South Korea placed, maybe almost nothing or very close to zero. So that means there is some issue when we think about the consumption of this rare earth element, and that relates to the production capacity. So if you see here, back to 1956, very small amount of RE produced over the world, less than 10,000 metric tons. But now it goes up more than 130,000, 140,000 metric tons of a rare earth element produced mostly from China, followed by United States and other countries. So this is very localized production and very important issue for many countries. So United States and also EU Commission, they categorize the importance of some materials in terms of supply risk. That means if some country fail to provide one of these material, we'll be in trouble. So rare earth element placed here very high supply risk, and also EU recognize same way this supply risk of this rare earth element very high, maybe on the top of the all other materials. So that give us some idea or warning how we need to manage or how we can make sure we continuously supply this material for our industry, right? That's a pretty much important step. So I'm looking for a little bit different aspect of our society, right? We produce a lot of material, for example, electronic material, product, computer, personal electronic device, mobile phone, monitors and televisions and scanner printers. All this, product contains kind of a metal and also sometimes a rare earth element. And if you see here, China produced almost, more than 7 million metric tons of electronic waste every year back to 2016. In United States, it's a second, and also there are other countries producing this electronic waste. And the problem is if we just waste this material and it goes to the landfill site, then that's all. That's the end of life of this material containing a lot of valuable materials. But there are other activities to recycle those valuable materials through some, purification, separation, extraction processes. And finally, we can get some, copper, gold, silver, platinum, or other material, of course, some water. So this is a very important concept for us, how we can face this situation. A lot of waste generated from our daily life, then that contains certain valuable materials, and how we can extract and reuse, recycle those material close to our daily life. And also, electric vehicle, use a lot of batteries, as we know, is inevitable. So, we may see a lot of more and more batteries comes to our waste side. So if you see here, market value of these batteries growing in the United States every year, we presume it will reach over $11 billion somewhere around 2027, will come soon, very soon. That means market size is growing rapidly. That means you may have a lot of waste coming from that industry after a few years. So to recover some valuable material from these batteries, spent batteries, typically we use 3 different approaches. One, pyrometallurgy, second one, hydrometallurgy, and the last one, direct recycling. Each approach contains some pre-treatment and some, roasting step or reaching step, and finally separation and recovery of some valuable materials. But this paper published in the Energy and Environment Science back 2022 this year, categorize this technology and analysis. Some, there are aspects like this. But what I recognized here, even all these technologies, processes matured, right? 5, 4, some technologies, lower maturity, but it's ready to use. That means this technology available for market. But the problem is if I see the quality of a recovered material is very low, right? Very low compared to other categories. That means we need to put our effort to increase the quality of a recycled material by precise separation, precise, recovery steps, something like that. So it'll be good take-home message for you if you are interested in this one. Even it's a mature technology, suffered from some precise separation and recovery of this valuable material. So you may think about how you can contribute to that area. And also, photovoltaic panels, more and more, PV panel used around the world to harvest the energy from sunlight. So we expect, we may have 4,500 gigawatt capacity energy generation from this solar panel by 2050. That means after a certain lifetime, you may have a lot of waste comes from this photovoltaic, energy harvest technology. Usually, we expect the lifetime of these photovoltaic panels about 30 years. However, for under some circumstance, like a hurricane, some earthquake, some undesirable event happen, then you may have this photovoltaic panel fully destroyed, and you may have a very short lifetime, even shorter than 6 or 7 years. Then, if you see here, how much photovoltaic waste can be generated from this country, maybe normal regular 30-year lifetime span, maybe China will produce 20 million tons of this waste. Then with a short lifetime, maybe about 13.5 million tons in United States and other countries. So this is a huge issue from this renewable energy sector. And if we see how much we can recover some materials from this photovoltaic waste, if we use a 1,000 kilogram baseline, then we have a 740 some shredded materials. It goes to landfill, right? More than 70% just goes to landfill. And maybe we can recover some material like a copper, 3.2 kilogram out of 1,000 kilogram, and aluminum about 171 kilogram, and some glass material about 63 kilograms. So if you see here, this is good, we can recover some material, but still we generate large, other material, more than 70% that goes to landfill. So maybe you can think about how you can replace this plastic or some, material, backbone material, environmental friendly chemicals, or some, biodegradable material to reduce the waste goes to the landfill. And also we can think about how we can reduce the step to recover this material from this photovoltaic waste. So I think there is huge, large space for scientists to contribute to save energy and reduce the greenhouse gas emission from this step also. Then so far I told about the mining and minerals and the resource recovery. Now I change my gear to water. Then if I introduce this graph, this is a very nice concept how our society linked each other. For example, water and energy, food is not individual one, is a linked each other, is a circulating as a one circle. So for example, we need clean water to produce energy. If water contains a lot of ions and other materials, they reduce the energy efficiency when they used for cooling or some other reactions. And also we need to provide very clean water for food and crop animals. So the water is kind of essential for me. So AWW, which is American Water Works Association, they created this nice banner like a no water, no shower, or no water, no beer. So how we can feel without water, our daily life is sustainable. So as you know, without food, we can survive more than 40 days, but without water, we barely survive about 3 days. So this is very critical, our life element. And if we see the quantity of water available around the water, this map summarizes that availability. So dark blue color indicating some countries has enough volume of water for their life, but some country yellow or orange means they suffered from water supply. So if you see here, less than 1,700 cubic meter precipitation per person per year, we defined this category as a regular water stress. And if that number down below 1,000 cubic meter per person per year, we define this country or this condition extremely water scarcity. If we see the number of South Korea, 2018, it's about 1,257. So already South Korea experiencing, very high water stress. And the United States, relatively, we have a very, plenty of water here, but the problem is it's unevenly distributed. So if you see here, some state in the United States, like a western side, this all the brown or orange color means annual precipitation less than 12 inches. Then if you see this green and blue color between somewhere around 36 to 80 inches precipitation, and this purple somewhere around, Washington State and close to Canada, more than 80 inches. So if you see, west and east, there is a huge difference in terms of, fresh water availability. So that's the very big issue for the United States. And here's my own analysis for the water price in the United States. So some states in the United States, like California and Florida, they use a lot of water for, agriculture. They grow, some almond, peanut, and orange, and some valuable, vegetables, and they use a lot of water. And then if they have surface water, which is A, or groundwater, which is B on this graph, they relatively has very, good price for the water to access the water, like 0.06 US dollar per cubic meter. So 6 cents or 7 cents US dollar per cubic meter of water. It's subsidized by government, but the problem is, if there is no water, no surface water, no groundwater, problems start. Because, very severe drought in western side, even you want to provide water from fresh water, there's no water available. Then we are looking for some, non-traditional water sources like a stormwater, treated wastewater, brackish groundwater, and seawater. Those are available, but if you think about the price of water, it goes up. So for the stormwater, $0.85 per cubic meter of water, and the brackish groundwater about $1.1, and the treated wastewater $1.7, and desalinated seawater about $2.0. However, stormwater is not available every time, right? If we have a precipitation, you can collect the water, you can provide, but sometimes you don't have any rain, then you don't have any option to use this water. And brackish groundwater, 1.1 US dollar per cubic meter, but still, when you have a severe drought, the level of groundwater decreased, and you have to go deep and deep to get this water, and the water price goes up. So I would think, this treated municipal wastewater and desalinated seawater can be possible, source for California, but still there are a lot of issues, so I'll explain that a little bit more later on. So if we see the water, this graph shows one very magnified water droplet. And I have a question whether if we compare this water back to 19th centuries and 21, so 20th century and 21st centuries. So whether we think this water quality is the same or not. Maybe it's not same as, back to 20th centuries. So if we see here, this water contains a lot of material like ions and also oil and other components like a contaminant of emerging concerns. You may hear about, pharmaceutical compound in water, also forever chemical like a PFAS compound in water, and a microplastic, nanoplastic, some other nanomaterial can be included in the water. And also there are a lot of nutrients. If we think about wastewater, there's a nitrate and phosphorus comes from our daily life, detergent and some other fertilizer, runoff from agricultural area that comes to municipal wastewater treatment plant. and you may have a lot of nutrient in the water, right? Then also there are a lot of pathogen. I'm not just talking about microorganisms, but I'm talking about pathogen, which is noroviruses or even coronavirus. Some other viruses can be included in the water. That will be a problem when we think about recycling and reuse of this water. So from here, I want to introduce my research interest and outcomes related to the research recovery and water quality issues to achieve that carbon neutrality and also mitigation of greenhouse gas emission. So this is a very typical or traditional approach, how our modern society use energy and water and resources for our daily life. So this is a very simplified images. So if you see here, we can start from here. Agriculture, activity or industry, they need some material. Industry, they need a rare earth element, they need heavy metals, and agricultural industry, they need a fertilizer, for example. That comes from our manufacturing facilities. And also they use a lot of energy. So we need a power plant, whether it's powered by nuclear energy or coal. So we need to produce the power plant power through some reaction, and that generates a lot of greenhouse gases. And we plugged our drinking water treatment plant and wastewater treatment plant to this power grid, and we treat the water. And desalination plant, desalinating seawater to produce fresh water, but still it requires a large energy. Also, it produces the greenhouse gases. So this is kind of a one-way traffic. Okay, we produce something from A sector, we send that material to different sector for different activities. And water treatment, we treat water and supply for industry and agriculture, and wastewater comes to wastewater treatment plant. And after treatment, it back to the ocean. Something like this is a one-way traffic, right? So if we see here how much carbon can be generated from these water treatment sectors, so drinking water, using coagulation, flocculation, sedimentation, and sand filtration, they produce about 0.46 kilogram carbon dioxide per cubic meter of water. And wastewater treatment plant, based on active sludge processes, about 0.38 kilogram CO2. And desalination using reverse osmosis membrane between 1.8 to 4.6 kilograms. So again, this is a one-way traffic. We use certain technology to treat water and desalinate seawater. Then we generate, we produce clean water, but we generate greenhouse gases, right? That's a one-way traffic. But if we make a link between different sectors, and encourage more circulation of this material, we call the circular economy, and also plug it in that renewable energy power grid, that helps us to reduce our greenhouse gases. So it is a proven concept, but how we can visualize or realize this one, that's our goal or our responsibility. So for example, industry sector, they use a lot of materials, and also that waste goes to the landfill side. However, we can recover this material, right, from industrial sector and back to somewhere in a city or other industry. And also municipal waste, solid waste, like a food waste or some other municipal solid waste, not just going to landfill. We can, burn that material, or we can think about how we can convert this waste to valuable material and energy. That will be a good approach for us for sustainable society. And also, some waste and also wastewater contains heat energy, so we can recover that heat energy from waste and water. That would be great to reduce the overall energy consumption, of course, a rare earth element. And wastewater itself, it contains carbon and nitrogen, phosphorus. So we can capture nitrogen and phosphorus, and we can back to that resource to the agricultural area, and we can grow some crops, and we can produce some bioenergy. And also, I believe some way we can convert carbon from municipal wastewater to biogas. Then we can generate further extra energy. So all these activities can be linked to each other very closely, creating some circle between different sectors, and that overall activity can reduce the energy consumption and further reduce the greenhouse gas emissions. Of course, encourage people to recycle material and energy. That would be great for our next generation. So inside of that overview, I have some research activities in my lab first one, we create some very interesting membrane which can separate microorganism pathogens from water, and also at the same time using some fancy carbon materials, we can provide heat energy through the surface area, and we can inactivate the microorganism directly on the surface of a membrane. So we use a polycarbonate membrane as an example. Then we provide electrical potential like a 10 volt, 15 volt, and 20 volt. Then we increase the surface temperature up to 83 degrees Celsius. We almost 100%, we inactivate one model bacterium like a Legionella. We achieved about almost 100% inactivation. So this is very good. When you think about the quality of water, you're concerned about, contamination by microorganism. So this membrane guarantees separation and also simultaneously inactivation of microorganism on the surface. And also in the United States, cyanotoxins from blue-green algae, like a cyanobacteria, is a huge issue. So even very low concentration, like part per billion microgram per liter level, it creates a huge problem. This is toxic material for human and animals, and even aquatic microorganisms. So few microgram per liter still create very huge problem. So a lot of state in the United States, when they have this cyanotoxins in their fresh water, they allow people don't drink water and boil water or get the bottled water, something like that. But this is a huge issue. So my lab, my research group contribute to fabricate some hybrid type membrane. It's made of carbon nanotube material and combined with the carbon nanotube and TiO2 nanotube together. So we'll create two different functions, one for porocatalytic degradation of these cyanotoxins, and also the cyanotoxins and the degradation byproduct can be absorbed by this material. Now we achieved almost over 95% of removal specific cyanotoxins generated from these harmful algal bloom issues. So if you need more information, I encourage you to check this publication from our group so you can see more details. And also we are thinking about how we can harvest or capture some valuable material from groundwater, because when we have a landfill, right, the landfill leachate goes to the groundwater, and the groundwater keep moving from one space to different spaces. So when we pump out this groundwater for agricultural activities, that groundwater contains a lot of emerging pollutant like PFAS, some other pharmaceuticals, heavy metals, and also some ions over there. So my lab designed like a flux redox flow desalination cells, and we try to clean out this material, and also we can recover, of course, some of them, and we create fresh water. The good thing is, by using this technology, we reduce the salinity below 500 milligram per liter with a very minimum of energy, about 0.5 kilowatt per cubic meter. So this is very comparable number compared to the reverse osmosis. So using less energy, we produce clean water from salty water, and also we can capture some valuable materials from that sources. So this is an ongoing study, so hopefully I can update later on. And also, if we are looking for municipal wastewater treatment plant, as it has some biological process. Finally, microorganisms, they degrade the carbon, converted it to carbon dioxide, and nitrogen and phosphorus from our household and industry. Mostly that goes to biosolid like a sludge, and we dispose or incinerate. However, if we think about how we can recover this nutrient, right, nitrogen and phosphorus, we may have a better chance when you think about this urine before it goes to the municipal wastewater treatment plant. Because if this nutrient goes to municipal wastewater treatment plant, and that will go to biomass sludge, and we send that biomass to landfill site, and there's no chance to recover. If we burn out in incinerator, it's not easy to recover nitrogen and phosphorus. So if we separate this urine from the point of generation source, production source, we have a better chance to recover this nutrient. It's a very high potential to recover this nutrient from the beginning of generation. So not only just the nutrient, also we can think about other heat energy in the wastewater, temperature a little bit higher than normal surface water because it comes from our daily life after shower or laundry things or industrial process generate a little bit high temperature wastewater. So we can think about even there's the low gradient, but still, we can harvest some energy and some valuable chemicals, and also rare earth element. So there's a large opportunities. One study from my own lab, we designed a membrane bioreactor system combined with magnesium carbonate material to capture phosphorus. So we have a municipal wastewater flows through this anoxic aerobic membrane bioreactor, and we immerse membrane module inside of this aerobic reactor, and we produced particle-free and bacteria-free water, and that water goes to a magnesium carbonate pellet to capture the phosphorus. And if you see here on the right top, this is the digital image of the material we fabricate, magnesium carbonate pellet. It has about 96 milligram phosphorus capture capacity per gram material. And when we apply this material here, very last stage here, then we can capture phosphorus from MBL effluent from this red color down to this green level. So the phosphorus from 2.0 milligram per liter to down to about 0.4 milligram per liter, difference will be 1.6 milligram per liter times the volume of water we treated. That can be captured by this material, and this is very rigid and very solid one. So we can put this material on the ground, and when there is irrigation or precipitation, water exposed to the material, then this material release phosphorus from the material. Then we can use that phosphorus for fertilizer. And this material, magnesium material, is an environmentally friendly material, and we can recycle this material, put it back into this column, and reuse for capture of phosphorus again. And lastly, my lab also thinking how we can harvest the energy from this water. So when we think about the mixing of two different stream having salinity gradient, one is a river water, low ionic strength, and the other one is ocean water, high ionic strength. It creates a salinity gradient. Then we can put that seawater and fresh water into this reverse electrodialysis system. Then we separate ions. So for example, cut ions comes to the left side, an ion comes to the right side through the ion exchange membrane. Then we create the chemical potential gradient, and using this redox couple based on the reduction oxidation reaction, we convert that chemical potential to electricity. So we published good papers recently how we can design this system. And also we fabricate some novel electrode material for this LED technology. Then we increase the performance and reduce the undesirable periodic reaction to prevent the scaling or fouling of electrodes. So we fabricate carbon nanotubes, and we fabricate two-dimensional, three-dimensional graphene materials, and we are using those materials for this LED technology to harvest energy from salinity gradients. So if you're interested, please check this publication. So with that, I'm gonna finish almost wrap up my talk, and all these activities I talked to you, grand challenges and opportunities, it comes to this journal section. So I started a new section in Chemical Engineering Journal about green and sustainable science and engineering. So we are talking about emerging materials and processes for green conversion of resources, and also system integration for renewable and clean energy. And also we want to advance treatment of air, water, solid with less carbon dioxide emission. Of course, resource recovery is a huge important issue for this one, and also energy, food, water nexuses. So we are aiming to innovate our science and engineering for sustainable future of human beings and nature. So if you're interested in one of these topics, if you're working on one of these topics, please submit your paper to us, then we will highly appreciate for your contribution. I think with that, I have to thanks to my previous and current student in my group, and a lot of students, undergraduate students, they come to my lab during summer and spend 2 or 3 months, contribute a lot. I couldn't list all of them, but thanks for them, and also my collaborator at the University of Cincinnati and different institutions and national government, federal government. Thanks to them. And lastly, funding sources from NSF and EPA, DOE, USGS, and also rural reclamation. So from also industry and the state of Ohio. So with that, I'm sorry, a little bit I was fast, but I tried to keep the time, maximum 40 minutes to give you more time for Q&A session, or you can have a lunch early. So with that, thank you so much for your kind attention. If you have any question, please let me know. Thank you so much.
Thank you very much for your very nice presentation. I personally think was really, really informative and was really great overview about this current status and the future of the technologies related to resource recovery from water and waste. Thank you very much again for a very informative presentation. And we have time for a couple of questions. So if anyone has any question about this topic and presentation, right? Please let me know. And then before going through the questions from the audience, can I ask you a very quick question?
Please.
Right, yeah. It's not really directly about your research, but as you know, I'm also very much interested in the area related to water, energy, and food nexus. So, and I also know that your university, the University of Cincinnati, is the home to the EPA, US EPA, the Cincinnati office, which runs one of the biggest federal R&D facilities in the state. So do you think there could be any opportunity for us to develop a kind of nice R&D collaboration among UNIST and University of Cincinnati and also EPA?
Oh, sure.
I'm very much interested in that.
So maybe, thank you for asking that question, Dr. Professor Lee. So maybe it will be very, very specific example for you. For example, EPA has a test bed at their local wastewater treatment plant. It's a federal facility, huge size. So they encourage us to come there, bring some novel technology to verify the performance. So for example, as I told you, the magnesium carbonate material is very simple chemistry. Then we validate that performance in the lab through a lot of batch ISO, some adsorption, desorption. We did that and we install semi-power plant on that test bed inside of that EPA test bed. We collaborating something like that. So why not? So for you, maybe some biogas or bioconversion, some biohydrogen production, or some resource recovery from municipal wastewater, industrial wastewater. Why not? We can talk. They are more than welcome to bring any novel technology and test with them. That's possible, doable.
Okay, that's great. I really hope to have a chance to talk more about this opportunity.
Sure.
Hopefully at UNIST, and it could also be in Cincinnati, right? So
yes. Why
thank
not?
you very much again. And I think it's almost the time to wrap up. And again, I really appreciate Professor Chae for sacrificing his evening time. Right?
It's okay. Just at 9 p.m. here,
Right. It's almost 10 p.m. there.
Right. Yeah.
Thank you very much again. And
No
I do hope to have another chance to invite you, hopefully in person. Right?
Sure.
So thank you very much.
Thank you so much. Yeah. So hopefully everybody in good health. Then I will see you next time again. Right.
See you next time.
All right. Thank you so much.